Welcome back to day number 2 of optimization. Here in number 4, we have a rectangle. It says it's located entirely in quadrants 1 and 2, so it's going to be above the x-axis the whole time, with 2 of its vertices located on that curve, y equals 64 minus x squared, which is an upside-down opening parabola. Find the area of the largest such rectangle. Well, of course, as always, the first step is to draw a picture, label the parts. So here's my picture. You can see the curve y equals 64 minus x squared is in blue. And the rectangle is in red. Now, that may not be the best rectangle. Maybe this green rectangle that's a little bit taller, it's got to bounce off the curve, bounce again and come back down. It's got to stay in quadrants 1 and 2. Maybe that's got more area than the red. You know, you're gaining this part. Of course, you're losing 2 parts of area on the sides. Maybe that's not as good. And I don't think I really drew it very straight anyway. But there has to be a rectangle that's the best. So let's say it's this red one. We'll keep it generic so that we're not making assumptions. This point that I'm labeling is going to be x comma y. But since the point is also on the curve, I can call it x comma 64 minus x squared. Because after all, if you're on the curve, y is 64 minus x squared, so right here. The other point will start with a negative x, but it will also end with the same 64 minus x squared. Okay, so that's the rectangle. We want to maximize its area to figure out what the x has to be for that to happen. So the area of a rectangle, the area of any rectangle, is length times width. The length is actually 2x. We have to go x in each direction. So that's the base, if you will. And then the height is simply going to be 64 minus x squared. I'm going to go ahead and distribute this. So we'll have 128x minus 2x cubed. We've eliminated a variable already by making that substitution on the graph. Now we just have to take the derivative. So area prime, A prime, is going to be 128 minus 6x squared. We set that equal to 0 and solve. Let's see, 6x squared is 128. If you divide that by 6, see, that's going to be 64 thirds. And if you take the square root of both sides, x is plus or minus 8 over rad 3. It does make sense that you had the plus or minus because we do have symmetry around the y-axis. I'll just go with the positive number. If you plug it back in to here, you can figure out what the area is going to be. So we have 2x. So that's going to be 16 over rad 3. And then 64 minus x squared. Remember that x squared is 64 thirds. So we have 64 minus 64 thirds. I'm kind of laughing because this is getting a little bit nasty. Oh my goodness. I think it's just time to use the calculator at this point. So we're going to give that a whirl. Let me type that in. And that's going to give me 394.138. If this was part of a free response question, College Board would also honor 394.137 because it's 0.1377838. So they'll take either 137 or 138 after the decimal. And that's the area of the largest such rectangle. Now, one way that you can make sure that that's a max and not a min, because you don't want to minimize the rectangle. That would be the worst thing ever. I think the minimum would come at the endpoints anyway. But let's take this derivative and take a second derivative of it. This is a really easy way to check, and I haven't really talked much about this yet. The second derivative would simply be negative 12x. And x is a positive number coming from here. Actually, x is a positive number both times because the negative is prefabbed on the front of it. And so negative 12 times a positive number is going to be negative. And if the second derivative is negative, you're concave down like a frown. So yeah, the critical point will be a max. So you have maximized the area of the rectangle, not minimized it. So that's good to know. So that's us sort of checking our answer. Okay, that's number 4. 3 more to go. Let's head forward. Number 5. Which point on the graph y equals square root of x is closest to the point 7, 1? I always like a picture. So y equals the square root of x would go through the point 0, 0, 1, 1. It hits 4, 2, 9, 3. Okay, so it's got some curvature to it. Typical square root looking graph. And of course the point 7, 1 just sits right here. So what point along that graph is closest to 7, 1? Well, you could head straight north, but that probably wouldn't be the best. I think you'd want to angle a little bit. Maybe go this way slightly. Maybe right to here. That might be a winner. Let's take a look here. This is, of course, is 7, 1. That's not going to change. And this point will be x comma y, which is pretty generic. But again, you're on the red curve, so y can be replaced with the square root of x. Okay, so far so good. Let's go ahead and make a formula from geometry. And actually, really, I think we learned this in algebra. It's the distance formula. Distance between two curves is a big square root. It's x2 minus x1 squared plus y2 minus y1 squared. Again, like I said, that whole thing is under a square root. It's really just the Pythagorean theorem, and somebody came along and square rooted both sides. It's just x squared plus y squared equals d squared. Because when you think about it, there's a kind of almost like a triangle here. This is x, this is y, and this is d. If you look at it like that, you're like, oh, that's not so bad. Okay? All right, let's start out with the x coordinates. We have x minus 7. And that's going to get squared. And then in the y coordinates, we have the square root of x minus 1, and that's going to get squared. Okay, so far so good. We want to minimize d because we want to minimize the distance of this segment because we want to get the point that is closest to 7, 1. Okay, so our goal is to minimize d, minimize distance. And to minimize something, obviously we want to take the derivative of it and set it equal to 0. But that derivative looks terrible because you have all that stuff to the half power. It's going to be nasty. I wish the square root just wasn't there. And so you know what? I'll get rid of it. I'll just bring this down without it. We'll minimize that, and that should do it. I know a lot of people are like, whoa, 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 wait a second. You can't just do that. You can't just take a square root off of some number or some expression. I'm like, yeah, that's true. That's bad math. Well, why did you do it? Because, friends, I don't need that square root. Let me show you why. I'm going to pick 2 random numbers. How about 3841 and 4175. Which one's larger? And of course the whole class is like, duh, it's the one on the right. I'm like, yeah, how big is it? Quickly! And nobody knows. And they're like, I don't know. I'm like, how big is this? And nobody knows. But you definitely know this is bigger. You're 100% sure. Yeah. How come? Because you looked inside at the radicand. You didn't need the square root to figure out which one was bigger. So if you want to make this entire thing as small as possible, don't you just really want to make the inside as small as possible? Yeah. So leave the square root off and make your calculus in your life easier. Okay, I got it. Great, let's move on. All right, to minimize, let's take the derivative. That'll be 2 quantity x minus 7 to the first. No chain rule on that because it's times 1. Plus 2 quantity radical x minus 1 to the first. But there is a chain rule there. The derivative of the square root of x is 1/2 x to the negative half. We're going to set that whole mess equal to 0. All right, let's do some math. Distributive property gives me 2x minus 14. I can't distribute here because of the negative second power. I can cancel the 2 and the 1/2. Now, you know what? I said x to the negative 1/2, and I wrote x to the negative second. Woo, that was almost a disaster. Hang on a second. Let's save that. All right, that looks a little bit better. Let's go ahead and move on. Okay, whew, crisis averted. Let's take the x to the negative half. Let's distribute it into the parentheses from the back and see what that does. We have x to the half times x to the negative half. That's x to the 0, which actually is just 1. And then we have minus x to the negative 1/2. Set that equal to 0. Not a whole lot I can do to simplify it. I mean, yeah, I can turn it into 2x minus 13 minus 1 over rad x. But I mean, I'm not going to be able to solve that. Not by conventional means. So I need to graph it. So I'll just graph it. I'll set it equal to 0. I'll see where it crosses the x-axis. Should be somewhere near 7, because again, I'm anticipating the answer to be right around 6 or between 6 and 7 somewhere. So yeah, I've got a good idea of what the graph's going to look like. Okay, I've got it typed in. Let's go zoom standard because I was stretched way out before. All right, there it is. That is between 6 and 7. Let's go second calc 0, number 2. Left bound, I'm just going to say 4. Right bound, let's call it 9. That way I don't have to trace, that's annoying. You want me to guess? Yes. 6.693. All right, so 6.693. I'm going to write that down. In fact, I'll write the whole thing out super accurately because we need the y-coordinate to stay accurate as well. And remember that y is the square root of x. So y is just going to be the square root of that number. I'll figure out what that is on the calculator. And that's going to come out to 2.587. We only have to be accurate to 3 places. So now that I've figured out y, I can round off the x to 3 places. I can get rid of the rest of this stuff. All right, notice that it says which point is closest to 7, 1. So I want to write my answer as an ordered pair and not just as x equals y equals. So just to make it look good. After all, the goal is to be impressive, right? So there we have it. That's the point that's closest to 7, 1. Okay, this is quite the question. Number 6, let's say that you and I are running a tour bus together. We need to have at least 40 people on the bus or we're going to cancel the tour for lack of interest. Normally, the tickets are $180 each. These people are with us all day. We give them lunch and dinner. It's a pretty good deal. We show them around town. But for each additional person above 40, we give everybody a $3 discount. So when that 41st person gets on the bus, everybody cheers. They're like, woo! Because they know that their tickets just went down to $177. All right, so you get the idea. There are $5,000 in fixed costs. So like gasoline, bus maintenance, I'm sure the driver wants to get paid, that sort of thing. And then every time we have another person on the bus, it costs us, as the tour directors, $18. Because, like I said, we're giving them lunch and dinner. I'm sure that the restaurants aren't going to give it for free. So we want to figure out how many people we want to have on this bus to do what every business wants to do, and that's to maximize profit. Okay. See, the problem here is if we let too many people on the bus, that $3 discount's going to kill us. If we don't have enough people on the bus, we could have done better. So where's the breaking point? Do we fill the bus? A lot of times you'll go to a concert or some sort of an event, and you'll see empty seats, and yet they'll claim it's a sellout. That's done very intentionally. Or maybe you get onto an airplane, and they're like, all right, seats are taken, everything's full, and you get on the plane, and it's not true. There's empty seats. Even though some people got standby tickets, and they got a deal at the airport, they could have let them on, and they chose not to. Interesting. All right, so maybe we want to leave empty seats on this bus. It's very possible. All right, let's figure out some equations. The first thing we need to do is figure out profit, because it says we want to maximize profit. And econ teachers are going to be very proud of me. I'm going to teach some econ right now. Profit is simply revenue minus cost. To give you an easy example of this, the high school I teach at has a store inside the school. And they sell, Diet Coke, and I buy a lot of it. and they charge me $1.50, for a 12 ounce, which actually isn't too bad. I'm sure if I went to the local, convenience store, it'd be more. But they probably got that pop for like 30 cents at a local wholesale club. So they're making, $1.20 on me every time I go in there. So the revenue is the $1.50 that I give them. The cost is the 30 cents that they had to pay to get the can of pop or soda. So yeah, okay. Cost is going to be easy here. Revenue will not be. So let's start with cost. Let's say that X is the number of people on the bus. Okay. And how many people should be allowed. We're solving for X. Find X in order to maximize profit. Well, the cost is easy. Every time a person takes the tour, it costs you and I $18 to, feed them and pay the admission to the, museums or whatever else. Plus, there's $5,000 in fixed costs whether anybody gets on the bus or not. The bus driver's salary, he gets paid whether people take the tour or not. Same thing with the bus maintenance and the gas and all that. All right, revenue. This is going to be interesting. Revenue is the amount of money that we have in the cash register, in the till. We said there were X people on the bus. That is true. And how much are these people paying? How much is each person paying? Well, they're paying $180 each. Well, unless there's a discount, the charge could be reduced by $3 if people get onto the bus. But we have to be careful here because it's not 180 minus 3x. That's not right. It's 180 minus 3 quantity x minus 40. Whoa. Didn't see that coming, huh? Maybe people did see it. That's impressive. All right, so X is the number of people. This is the price per ticket. I'll abbreviate that. So you think about it, if 40 people take the tour, we'll run the tour, but everybody's going to pay $180. It'll be 40 times 180. The discount will be 0. 40 minus 40 wipes that discount out. Whereas, let's say 48 people ride the bus. Now I'm giving out 8 $3 discounts. Okay, so everybody gets, $24 off their ticket. And now I'm starting to get nervous, like maybe we shouldn't let more people on. Okay, so that is the proper formula. Now don't panic. College Board is not going to make you come up with a formula that difficult because this is a calculus exam, not a formula writing test. So usually they'll give you the formula or it'll be very easy to find. So I just figured I'd challenge you on one here. Let's clean this up a little bit. This is negative 3x. Negative times negative is positive 120. There's also a 180 there. So that bracket is simply going to be 300 minus 3x, which looks a lot better. There's still an x in front. We can do distributive property here. We can also do it here with this negative. So we're going to have 300x minus 3x squared minus 18x, I'll combine the like terms in a moment, minus 5,000. That's the equation for profit. And that is the thing that we want to maximize. All right, I'm going to combine the like terms as I mentioned. We have 300x minus 18x here. If you combine those, that's going to be a nice healthy 282x. So let me just rewrite this. All right, variable's been eliminated. Equations are written. It's time to take a derivative. Profit prime. That's going to be negative 6x plus 282. Set that equal to 0. Can add 6x to both sides. You're going to get 6x equals 282. And 282 divided by 6 comes out to 47 passengers. So you want to ideally have 47 people get on the bus. The moment that 48th person gets on, you're like, no, the bus is full. And they're like, I see empty seats. And they're like, it's full. Pull away. Shut the door. Okay. Let's graph just to make sure. I'm going to go ahead and graph the profit equation. And you should be able to see that 47 will be the max. I don't know if you noticed or not, but that $5,000 in fixed costs, that didn't really matter. If there's extra fixed costs, we typically don't pass that on to the customer in the price. That won't help our overall bottom line, even though a lot of companies do that. All right, before I hit graph, well, let's hit zoom standard. We probably won't be able to see much because we only go out to 10. And remember, we're not running the tour without 40 people on the bus, so that's not going to show up. Let's go to window. Remember, X is the number of passengers, so the minimum is 40. We think that 47 was the max. That was the answer that we got. So let's go from 40 to, say, 60. That way we can see the curve. And Y is actually the profit. We know we're going to make some money, so let's not make the minimum negative 10. We're not losing money on this thing. I don't know. Let's start with maybe $1,000 and go up to $2,000. I'm just guessing. This may be stupid. I may have to redo it. Let's just see what it looks like. Oh, that's not bad. Okay, got a little lucky. Let's go second calc maximum. That's number 4. Left bound. Enter. Right bound. Let's make sure I'm safely past it. Heading downhill. Yep. Guess. Look at that. 47 people on the bus. And that'll give us the maximum profit of $1,627. Let me hit the table for a second. Second table set. Let's start at 40. We'll go by ones. You can see that if we let 40 people on the bus, we'll make money. We start making more money and we start letting more people on until we get to 47. Once that 48th person gets on, we're like, oh, no. We start to lose $3, and then we start to lose 9, and then 15, and we're like, shut the doors. Okay, so if the bus holds, 60 people, we don't want to fill it. We want to try to get 47 people on this and then take off. Interesting. The power of calculus. Okay, last but not least, you're a motorist in the desert in a car. Your car can only go 30 miles an hour on the desert, and it's really, you're trying to move, but the sand is just thick. Once you get onto the road, this car will go 75 miles per hour. All right, which route should the driver take in order to get to point B as quickly as possible? And it probably won't be the shortest route, because the shortest route to B would just be to stay in the desert the whole time. And at 30 miles per hour, I just don't think that's going to cut it. I think you want to go 75 at least part of the way. Now, you could also go straight to the road, and then that way you'd be able to go 75 miles per hour a lot longer. But you know what? Straight to B from the car is about 12 miles using Pythagorean theorem. Do you really want to go 17 miles, part of it through the desert? I don't know that that's the best. The best way almost always is to kind of take a bit of an angle, like the dotted line, and go from there. And if it's not the best, what will happen is calculus will tell us so. All right, I'll show you what I mean here. Let's start out by labeling the parts of this drawing. I'm going to call this distance right here x. And x will be our answer. We'll say, hey, we have to aim for 3 miles down the road, or 3.2 or 5.1 miles down the road, and then drive the rest of the way to B. And the rest of the way is 9. Minus that x I don't want, right? Because the whole thing's 9. That way x and negative x cancel, and it adds up to 9. Okay, we can also figure out the dotted line using Pythagorean theorem. We go x squared plus 8 squared, and we square root it. Okay, so a little Pythagorean theorem gives us that. And the route that I propose that we take is this one. So we have to figure out how long is that going to take, because getting there as quickly as possible means we want to minimize time. And so we need to come up with a time equation. And there's not a single time equation in geometry. There's no equation in the book that says time equals. So we have to come up with one, and so therefore I'm going to science. In my good old science classes, we learned that rate times time equals distance. I can still hear my teachers saying it. Since we want an equation for time, I'm just going to divide both sides by r, divide by the rate. Time is the distance you traveled divided by your rate or your speed. So the time that this car is taking to get to town B here, first of all, it starts out in the desert. So that's going to be x squared plus 64 to the 1/2 power, because that's a square root. That's the distance. But the rate, since you're in the desert, is 30 miles per hour. Plus, because it's going to take you more time. You're not to town B yet. Now you're on the road, and you have to go another distance of 9 minus x, but now you can go crazy and go 75 miles per hour. So we have ourselves a time equation. I'm going to go to another sheet of paper just so I have plenty of space for this one. And when I do, I'm going to call this 1/30th, and I'm going to call this 1/75th. I think that'll be just easier for people to deal with. All right, let's make some room. Okay, it's time for a derivative. That would be time prime. Not prime time, but time prime. 1/2 times 1/30th is 1/60th. Using the power rule, x squared plus 64 goes down by a full power. Times the chain rule of 2x. Over here, this is 9/75ths. You know what the derivative of 9/75ths is? Yeah, it's 0. So I'm not going to write anything. Minus 1/75th x, that's going to be minus 1/75th. And we want to set that equal to 0. All right, this will not be solvable by hand. See, we will have to do some graphing. Tell you what I'm going to do. I'm going to kick the 1/75th to the other side where it will be positive 1. I'm going to reorganize the other side into a fraction as well. We can cancel a little bit here. This 2 into the 60, it'll be a 30 instead. So we have this x holding the forward up top in the numerator. And then in the denominator, we have 30 times the square root of x squared plus 64. And hey, algebra students, yeah, I shouldn't have to say this, but that's not x plus 8. Don't be that person. Okay. Oh, man. Cross multiplying. We're going to get 75x equals 30 times square root of x squared plus 64. Theoretically, you could square both sides. Let's do it. 75, well, you know what? Let's not do it. Let's divide by 30 first. Because 75 divided by 30, I can simplify that. That'll make the squaring a lot easier. If you divide those both by, heck, you can divide them both by 15. That's a 2. That's a 5. That goes all the way down to 5/2. There we go. Now we're talking. Now when I square both sides, I don't have to think so hard. Okay, let's get everything together. I'm going to subtract x squared from both sides. Although this x squared has a 1 in front of it. Let me write that 1. Do you like my 1? Yeah. All right, let's take away 4/4 x squared from both sides. That's going to make the left-hand side 21/4 equals 64, which I'll make into a fraction. We'll multiply both sides by the reciprocal, which will be 4/21. here's where the fun's going to end. I'm going to have a calculator because I'm decent at mental math, but I'm not that good. I do know 64 times 4 is 256. Yeah, that's the end of the line for me. You square root both sides. Now, obviously, we don't need the negative because we're not going to go negative. We're not going to travel away from town B on the road. So since this is a word problem, I don't need that. The square root of this, we'll grab on a calculator. Square root of 256 21sts is 3.491. That'll be miles, because this problem is in miles per hour. So we want to aim 3.491 miles up the road. So almost 3.5 miles. There's my answer. Now again, a lot of people might be cynical and they're like, if you want to go quickly, you wouldn't be doing calculus in the desert. I'm like, okay, yeah, fair point. You know, that's true. That's true. But, you know, what if you're a company like UPS or FedEx or even Amazon, and it's not a desert, but you just want to get to town B as quickly as possible, and you do this route over and over and over and over. Then you do calculus once and you figure out where you should aim, and, you know, you can make yourself efficient. And this can be done many different times, and you really start to save a lot of money. So there are uses for it, even though the problem might be a little goofy. All right. Well, you know what's not goofy is the fact that we're done. That feels great. We got through optimization, which is a challenging section, but it's kind of cool. You can see the power of calculus in real life. So until we meet again, take care. See you later.